So as you may have seen in the reading, Chapter 2, Section 6 is kind of lengthy. We're going to be talking about chemical symbols, specifically chemical formulas and chemical equations. So first thing is formulas for chemical compounds. A chemical formula or a molecular formula, basically it's a written combination of all the symbols that represent the atoms combined in a chemical compound, such as nitrogen, N2, or sucrose, C12H22O11. These little numbers right down here, the numbers written below the line, are called subscripts. They indicate or they tell you the relative amount of atoms of each kind. Basically, they're telling you how many of that kind of atom are there. So for example, for the nitrogen, there are 2 nitrogens. In sucrose, there are 12 carbons, 22 hydrogens, and 11 oxygens. Another way to write a formula for chemicals is to make a structural formula. What this does is it actually shows the connections. It shows where the atoms bond with each other. Usually this is represented as straight lines. So as here, you can see that the oxygen and hydrogen bond right here. This oxygen and hydrogen bond, it's the same oxygen. This is water. These dots right here represent lone pairs of electrons. Again, this is not something you have to know right now, but just know that this is called a structural formula. And where the two different kinds of elements meet is called a bond, and it's represented by a straight line. And you go, that's diagonal. It's straight. Here's another example. This is ethane. So again, you can see where all the different hydrogens bond with each of the carbons, except right here, 2 carbons bond together. So again, chemical formulas or sometimes molecular formulas are the element symbols and the subscripts. Structural formulas are the symbols, but then it shows you where they actually bond. Organic versus inorganic. You might have heard organic life and inorganic things. Organic just means it's basically anything of a carbon. It's substances based on carbon and hydrogen. Now, it does not have to be just carbon and hydrogen. Yes, methane, which is farts, that's what makes farts smell, is your methane. It is just carbon and hydrogen. But caffeine, on the other hand, it's a carbon structure, even though you can't really see these carbons everywhere in these corners, right here, 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 and here. These are actually carbons. They save writing and save room by not actually putting them in there. There's carbons here, but notice it's not just carbons and hydrogens. There's oxygens, there's nitrogens, but if there is a carbon, it is typically considered to be an organic compound. Inorganic then means that there are no carbons. So for example, sodium chloride. Now be careful, that's chlorine, not carbon. It's sodium chloride. There's no carbons, that's table salt. So anything that does not have carbon is considered inorganic. Pretty easy difference. Chemical equations now. Again, we're not at the point where we have to hardcore balance. You have to be able to identify if an equation is balanced, but let's talk about what that is. A chemical equation represents a chemical reaction by writing down the reactants and the products. And we'll talk about which is which here in a little bit. Specifically, we want to look at balanced chemical equations. It's an equation where the total number of atoms on each side, reactants and products, for each kind of element is the exact same. So, for example, there are 2 carbons on, this is known as the reactant side, which we'll get to. There are 2 carbons on the reactant side. There are 2 carbons on the product side. There are 2 oxygens on the reactant side. There are 2 oxygens on the product side. That would be a balanced equation. These big numbers in front are known as a coefficient. It's a number written before a formula to balance the equation. It also tells you the relative amount of substances involved. These coefficients are actually very, very important. So what this says is 2 molecules of carbon will react with 1 molecule of oxygen, and it will form 2 molecules of carbon monoxide. So whenever you have 2 molecules of carbon, it takes only 1 molecule of oxygen to make 2 molecules of carbon monoxide. So that's what that says. It's basically a 2-to-1 ratio between carbon and oxygen. And again, you don't have to technically balance these yet, just be able to say, oh yeah, this is balanced. And we'll look at another example here. So what are some characteristics? What are some important things about chemical equations? First is all the reactants and products must be identified. That's basically a very fancy way of saying you have to have the exact same kinds of elements on both sides of the equation. Notice I have carbons on the left side, which is the reactant side. That means I have to have carbon on the product side, the right side. I have oxygen on the left. I have to have oxygen on the right. Now, if for some reason there was a magnesium that popped up on the product side, but there's no magnesium on the reactant side, that's not possible. It's impossible. You can't do that. It's like putting in a turkey in the oven and then you pull out a pepperoni pizza. It doesn't happen. Okay? You can't start with one thing and make something totally different. You can't do that in terms of elements. So whatever kinds of elements are on the left side, you have to have the same kinds of elements on the right side. The equation must contain the correct formulas for the reactants and products. Okay, you have to balance the equations, which again, something we'll deal with later on. And it also says the law of conservation of mass must be satisfied. And this is actually two kind of things going on here. First is the total mass has to be the same. So let's say I have 50 grams of carbon and I have 25 grams of oxygen. If that's a total of 75 grams on the left side, that means I have to have 75 grams on the right side total. So again, the total mass on the left side has to equal the total mass on the right side. Both sides have to have the equal mass. It's also saying that the equations need to be balanced. You have to have the same number of atoms of each element to be correct on both sides. Now, notice that it's 2 carbons, 2 carbons, 2 oxygens, 2 oxygens. They don't all have to be 2. That's just a coincidence in this example. Parts of a chemical equation. Here we go. So, this will give us a better idea of what I'm talking about when I say they don't all have to be 2. We have magnesium plus hydrochloric acid yields hydrogen plus magnesium chloride. The red side, the side that's on the left, are known as the reactants. They're the things that will react together. That's why they're called reactants. They're what react together. The right side are the products. They are the element, or not elements, it could be element. They are the substances you create. You produce them. The arrow stands for yields, produces, creates, etc. Looking at the thesaurus. An S, like you see here, stands for a solid. A G stands for a gas. An AQ means aqueous. I've also heard it called aqueous, your choice. Basically, that means it's something that's dissolved in water. Whenever it's aqueous, it means it's dissolved in water. If it was a pure, like it was pure hydrochloric acid, then it would be an L for a liquid. But this represents that this is hydrochloric acid that was dissolved in water, hence why it's called aqueous. This is magnesium chloride that's dissolved inside of water. That's why it's aqueous. And that's it. Again, there's a lot to Chapter 2, Section 6, so please make sure you go back through the reading in that, and we will discuss it sometime in class.